Hi, everyone. Thanks so much for joining us this evening. We have a very special event titled An Evening with Webb for you tonight. My name is Natalie Willett, and I'm the coordinator of the Institute for Research on Exoplanets at the Université de Montréal. But more importantly, for tonight, I am also the outreach scientist for the James Webb Space Telescope in Canada. Before we begin, I would like to take a moment to acknowledge that the land upon which the Université de Montréal and other academic institutions in Montreal are situated is the traditional territory of many Indigenous peoples who are the custodians of these lands and waters. Tiohtià:ke has long been a gathering place for diverse First Nations of the Haudenosaunee and Anishinaabe federations long before the arrival of the French. We are grateful to have the opportunity to live, work, collaborate, and learn here, and we respect the continued connections with the past, present, and future in our ongoing relationships with Indigenous and other peoples within the Montreal community. I invite all attendees tonight, wherever you are, to reflect on the land upon which you are located and the relationships you have to the communities that have inhabited it and continue to inhabit it. Tonight's event is organized jointly by the Institute for Research on Exoplanets and the McGill Space Institute. There you go. All right, had to move. I've never organized an event with so many guests and slides, so you'll see a lot of movement going on tonight. Both institutes bring together world-class students and researchers from all over the world to study the wonders of the cosmos, ranging from exoplanets, of course, for IREX, to the very beginnings of our entire universe. So lots of different subjects covered by both institutes. Both institutes also have very strong mandates for education and outreach and are national leaders in the communication of astronomy to the public. It's my absolute pleasure to be your host tonight on behalf of IREX and MSI, as well as all contributing partners to the James Webb Space Telescope. We actually chose this week for our event to time it with the World Space Week going on all throughout the week. There are events happening all throughout the globe. And this year's theme is Women in Space. And you will notice that the makeup of our panel tonight reflects that, but it wasn't even intentional. There are just so many talented and inspiring women to pick from when you talk about astronomy in Webb that we just happen to have an all-female panel tonight. I'm going to begin tonight's event with a brief overview of the Webb telescope, what makes it so amazing, what its scientific goals are, and Canada's role in the mission. Each of our panelists will then briefly go over what they plan to do with the very precious telescope time that they snagged in a very competitive process for Webb's first year. We'll then move on to a panel discussion with all three of our panelists. And finally, we'll open the floor up to you, our audience, and let you ask all your questions to the panelists. We're with you tonight on both Facebook Live and YouTube Live on both IREX and MSI channels. If you haven't already, I encourage you to like and subscribe. Feel free to chat with us in the comments and chat throughout the event. We have three wonderful moderators with us tonight, working behind the scenes, Marie Evenot and Frédéric Baron from IREX, and Carolina Cruz-Venaccia from the MSI. If possible, we ask that you ask your questions towards the end of the panel discussion or during the audience question sessions so we have an easier time to find them. So without further ado, let me jump right into Webb. So I like to talk about astronomy as the oldest science. We've been doing astronomy for millennia because we basically just need our eyes and to look up at the sky. But over time, we have developed instruments and telescopes to perfect astronomy and astrophysics and really understand what's going on in space. So I can't talk about space telescopes without mentioning the Hubble Space Telescope that you can see here. Hubble was a revolution in astronomy and space astronomy and has made wonderful discoveries and also importantly has made a really big impact on the public's perception of astronomy. So you can see here just a few images taken by Hubble that has been very, very popular over time. But this is a mission that's been going on for over 31 years now. Some of you who are older may remember that Hubble had rough beginnings and there were issues with its mirrors that made the first images coming out of Hubble not so good. Luckily, it's in low Earth orbit, just a few hundreds of kilometers above our heads, which means that we were able to send up astronauts to actually fix the mirrors and make sure everything worked well. And the Canadarm was actually really important in those missions to fix the mirrors on Hubble. But this mission is getting older, the technology is getting older, and we are no longer committing to making major reparations and repairs on Hubble if something were to happen. So we have to start thinking about a successor. for the Hubble Space Telescope. And we like to say successor rather than replacement, because ideally Hubble will continue functioning, continue working, and both space telescopes will be able to work together over time. So the successor for Hubble is named the James Webb Space Telescope. And you can see here, it already looks very, very snazzy and very, very different from the Hubble Space Telescope. And I'll mention a few key differences between the two missions. This is an international collaboration led by NASA with very strong contributions from the Canadian Space Agency, which is exciting for us here in Canada, and the European Space Agency. And I'll mention some of the contributions of these different partners here. So my role in the mission is an outreach scientist in Canada. And I really love my title because I find it's so descriptive about what I do. So I am an astrophysicist by training. I have a PhD in astrophysics. I am part of the science team with Webb, but I act as a bridge between the science team and the general public. So my job is to do outreach, make sure that as many people as possible are aware of this mission, understand why it's such a fantastic mission, and they know the great science that Webb is going to be doing because your tax dollars paid for the Canadian contribution on Webb. So you can see me here, a picture of me visiting the telescope in California a few years ago, although soon it will no longer be there because it won't actually launch from California, and I'll tell you a little bit about that in a moment. So Hubble is really the standard when we talk about space telescopes, but we're hoping Webb to blow it out of the water in lots of different components. So these are two images, two representations of the Hubble Space Telescope on the left and the James Webb Space Telescope on the right. And you can already see that the James Webb Space Telescope is much, much larger. So typically in astronomy, when we talk about the size of a telescope, we really care about the size of its mirror. So Hubble has a mirror that's 2.4 meters wide, whereas Webb, you have a mirror 6.5 meters wide. And that only sounds about twice as big, but actually it's nearly 6 times as big because what's important is the surface area of the mirror, not only the diameter. So that is one key difference. Hubble will be more sensitive and larger, so it's able to capture more light and it'll be able to look at objects that are fainter and farther away from Earth. So lots of discoveries to do there. You can also see a really big component on Webb here is its sun shield. And I'll talk a little bit more about how that's important. But that sun shield is the size of a tennis court. So really, really huge, which was a really big challenge for the engineers building this telescope. Another key difference between the two telescopes is the type of light that they can look at. Hubble, I like to describe it like a really big human eyeball. It can look at the same kind of light that humans can, whereas James Webb can look at a type of light called infrared light, which is invisible for humans. And I'll talk about what you can see in infrared light and why it's really important to consider that part of the universe. So you might have heard of Webb before, and one of the things you've heard of is, of course, some of the delays that has gone through with the mission, but this is really, really important to hammer home. Hubble had issues at the beginning that we could fix because it was close to Earth, but Webb will be launched very far away from Earth, 4 times farther than the moon is located, actually, 1.5 millions of kilometers away. So if something goes wrong with the mission, we cannot fix it. So Webb has gone and undergone very important tests to make sure that it can survive the very harsh environment involved in launch and also its operations through space. So you can see it here in a lab where it's about to be put into a vacuum chamber, which simulates the environment of space. It also had to undergo very, very violent vibration tests and acoustic tests where it's being shaken up to simulate the environment of a launch on a rocket to make sure it can survive. So when there were delays that were being announced, it was to make sure that everything worked perfectly because we only get one shot with this telescope. So currently, I'm very happy to say that all of the tests have gone well. They're all completed. The telescope is now in what we call its stowed configuration. So it's all packed up in a nice little package. It'll be shipped very, very soon, and it'll be ready to be launched shortly. So it's going to be launched not in California, where its most recent testing has been going on, but in South America, in French Guiana, in a town called Kourou, in the Guyana Space Center. So this is where the European Space Agency performs many of their launches. And the type of rocket that will be putting Webb into orbit, called Ariane 5, will be launching from there. So you can see its journey there. It'll be going on a boat through the Panama Canal to its final destination. Well, not its final destination. Space is its final destination. To its final earthly destination at the Guyana Space Center, where it will be put into an Ariane 5 rocket. But I mentioned how large this telescope is. It's humongous. So it actually needs to be folded up into a tiny little package, like a piece of origami, to be put into the rocket to be then launched up. So once it goes up in the rocket, of course, it needs to deploy. So over the course of 14 days, while it is moving to its final destination, 1.5 millions of kilometers away from Earth, it will be unfolding throughout that whole process. So you can see here, and you can actually track at the bottom here, you can see its movement along the orbit, and it'll eventually cross the moon of the orbit and eventually go 4 times farther than the distance of the moon. And while it's moving, its solar panels will deploy, its communications antenna will deploy, its gigantic solar panels will deploy. So the solar panels are very important because I mentioned this is an infrared telescope. So when you think of infrared, often you think of a science fiction movie where people have infrared goggles on and they're looking at animals or people in the dark and they can see humans glowing. So we often associate infrared light with heat, and what heats us up? The sun. So we do not want the sun to heat up the telescope itself, because if it did, the telescope would produce its own infrared light, its own light pollution, which would not be good news. So the solar shield, the sun shield, is the equivalent of putting on sunscreen with an SPF of 1 million to try to block out the heat and the light from the sun. So it's a very key component of the observatory. On the cold side of the telescope, you'll have the mirror and all of the scientific instruments kept cold, and so they won't be producing their own heat. So a very complex deployment going on while it's moving in space. So why infrared light? So I mentioned that the Hubble Space Telescope was looking at visible light. James Webb will be looking at infrared light. So that is redder than red, is another way that you can think about it. And we often associate it to heat, and it's invisible to humans. But lots of different things in space radiate infrared light, and we'll talk about some of those things with our panelists tonight. So planets are something that radiate very strongly in infrared light. So this is a picture of Jupiter taken by the Juno probe in infrared light. Solar systems being formed and certain type of very common stars called red dwarfs are also very bright in infrared light. You can also study the earliest galaxies in the universe. They were not initially shining in infrared light, but because their light has been what we call redshifted due to the expansion of the universe, by the time the light reaches us or the telescope, it has become infrared light. So lots of different things, scientific missions that the telescope will be able to do in infrared light. Another reason why infrared light is very important is because the universe is a very dusty place. So this is a very iconic picture taken by the Hubble Space Telescope in visible light of the pillars of creation. And you can see here dust that is occurring, that happens in a star-forming region. And visible light cannot punch through dust in space. Unfortunately, infrared light does go through this cosmic dust. So by looking at the same exact region of space in infrared light instead, you can actually see lots more information going on, lots of different stars and everything that's hidden behind that veil of dust. So there are 4 scientific instruments on the Webb telescope, different combinations of cameras and spectrographs, which can break up light into a rainbow. The one I really want to focus on is FGS NIRISS, which is a double instrument, and that's the Canadian contribution to the Webb mission. So this is it here. It's about the size of a washing machine, and it's 2 instruments in one. One is called FGS, or the Fine Guidance Sensor. It's a camera that is used for every single observation made by Webb to make sure that the image is very crisp and clear and the telescope is stable and pointing towards the object of interest. The other one is called NIRISS, or the Near Infrared Imager and Slitless Spectrograph. It is a great tool to study galaxies, but also especially exoplanets. And I will let some of our panelists talk a little bit about that. So the lead on this was the Canadian Space Agency with lots of different partners, including lots of people at IREX at the University of Montreal. So in exchange for all of this great contribution that we gave to the Webb mission, we're going to get at least 5% of telescope time on Webb. That'll be given to Canada. And this will be split between lots of different projects, including 450 hours of what we call guaranteed time observations. So this is time that has already been allocated. We have really interesting projects ranging from very distant galaxies to solar system objects to exoplanet atmospheres, lots of different things. We also recently found out that 14 proposals for a total of 331 hours led by Canadians were awarded time during Webb's first year of operations. And you will be lucky enough to hear from 3 of those proposal leaders tonight. And there are 72 more proposals with Canadian collaborators. We also have one other project related to early release science program. This is like the first science that's going to come out of Webb, that's co-led by Canadian astronomer Elf Peters at the University of Western Ontario. So this is a very, very whirlwind tour of why Webb is so incredible, what Canada did to be involved. And I have to emphasize, Canada was not involved in the Hubble Space Telescope, but it will be involved in the Webb Space Telescope. I'm personally super, super excited for it. So to continue on with the event, I am happy to introduce our first panelist, Lisa Dang. She's a physics PhD candidate at the McGill Space Institute and IREX, so she's double dipping tonight. She is a member of both institutes that are organizing. During her graduate degree, she also held a research position at the NASA Spitzer Science Center, so she's familiar with infrared astronomy, at Caltech in Pasadena, California. She studies the diversity of exoplanets and their climates with a variety of space telescopes, most excitingly with the upcoming Webb telescope. And she hopes to understand how planets form and evolve to ultimately uncover the recipe for habitable planets. So she'll talk a little bit about her research project that is going to get time on the Space Telescope.
Thanks, Natalie, for the very nice introduction. So my program is titled A Hell of a Phase Curve, where we aim to map the atmosphere and the surface of a lava planet. So the lucky lava planet that we're going to observe with James Webb is K2-141b, one of the most extreme places in the Milky Way. On top of being a lava planet, it's also commonly referred to as a super Earth, and that's because it has 5 times the mass of the Earth, but it's also slightly bigger than the Earth if you compare it right here. So not only that, it's also so close to its parent star that it only takes 7 hours for this planet to complete a whole tour around the star. So this means that a year on K2-141b is only 7 hours. And if I were to live there, I'd be celebrating my, 35th 700,000 birthday right now. It's also locked to its star in a way where one side of the planet is sort of permanently facing the star and the other side is permanently dark. So this means that if Montreal were here, it would be permanently nighttime. And if I wanted to see the sunlight, or rather the starlight, I would have to travel all the way to Vietnam to see the sun, but also this place would be sunny and very hot all the time. They wouldn't know what night is. Actually, it would be so hot in Vietnam that it's going to reach temperatures of 2,000 degrees Celsius, to be precise. That's hot enough to melt our continents into magma oceans. And so the atmosphere would be made from evaporation from these magma oceans. And so you would have atmosphere made of rock material, but also clouds made of rock material. And so when I say that I want to map a planet, what we're hoping for is a map that's looking like this, where you can see the temperature at different location. This might look like some of the things that you see on the Weather Channel. So you have different temperatures at different location. You also know the wind at different locations. So you can sort of predict where it's going to be cold, when it's going to be hot. On Earth, it's easy to do this, or not really easy, but the way that we do this is by sending satellite around the Earth, and then the satellite goes around the Earth and takes picture at different location. We're not fortunate enough to have James Webb orbiting all kinds of exoplanets around here. So instead, we're just looking at these planets from far away with James Webb. And the difference here is that instead of orbiting around the planet and taking pictures at different places, what we're going to do is we're going to wait for the planet to orbit around the star and take pictures of different faces of the planet to ultimately recover a map of the planet. So this is my program. And I just wanted to take some moment to say, this is not a one woman's job, but rather it wouldn't be possible without the contribution of all of my collaborators. So to make sense of our James Webb observation, this requires input from both observers like myself, but also theorists to help us understanding what we're seeing. And so you can see here that our collaboration is including people from all around the world. And so this is my proposal.
Natalie, you're muted.
Thank you so much. Thanks for letting me know. So our next panelist that I'm happy to introduce is Olivia Lim. She's a PhD student at the Université de Montréal, who's interested in the TRAPPIST-1 system, very, very popular in the media, but also in astronomy, of course. It consists of 7 Earth-sized exoplanets orbiting a red dwarf star. Olivia is currently studying the geometry of this system to understand how it may have formed, and she's looking forward to learning more about exoplanet atmospheres with the James Webb Space Telescope.
All right. Hi, good evening, everyone. So yeah, our team and I submitted a James Webb proposal to observe an exoplanetary system that's become very close to my heart over the past couple of years, and it's the TRAPPIST-1 system. So TRAPPIST-1 is an exoplanetary system that's located at about 39 light years away from us. So it's not within our reach in the sense that you probably won't be able to travel to TRAPPIST-1 for the next couple of years or decades, but that's not a problem. There are so many other reasons why we should be interested in TRAPPIST-1. So the first thing, as Natalie said, TRAPPIST-1 has 7 rocky exoplanets orbiting a red dwarf star, as we can see in this artistic representation of the system. And all 7 of those planets have approximately the same size as the Earth, so that's very cool. Another interesting thing about the system is that we know that some of the planets in the system are in what we call the habitable zone of the system. So the habitable zone is the region around a star where a rocky planet can have the temperature that's just right to have liquid water at the surface of the planet. So that's very interesting, but there's even more to like about TRAPPIST-1. So those 7 rocky exoplanets don't just orbit the star in any random direction, they all transit the star. So what that means is that if we look at the TRAPPIST-1 system from Earth or from the James Webb Space Telescope, we'll see that the planets all pass in front of the star periodically. And that's a very good news for us because it allows us to do something called transit spectroscopy. So transit spectroscopy is essentially a technique that allows us to study the atmospheres of exoplanets. So I'm going to try to explain transit spectroscopy in one slide. If you just imagine a simple planet, kind of like our own planet, the Earth, with a thin layer of atmosphere around it, you'll see that if the planet transits the star, so if the planet passes in front of the star, a part of the light of the star will go through the atmosphere of the planet in these small regions. And so the light from the star is going to get filtered by whatever is inside the atmosphere of the planet. And so when we receive that filtered light on our telescopes, we can disperse the light, or in other words, we can split the light into its different colors or wavelengths if you prefer, It's exactly like when a ray of sunlight passes through a prism, and then we get a beautiful rainbow on the other side. So this beautiful rainbow is what we call a spectrum, and in this case, it's called the atmosphere spectrum of the planet. And it's very useful because it contains information about, for example, the different molecules that are inside the atmosphere of the planet. And so this is what we call transit spectroscopy, and this is what we propose to do with our James Webb proposal. So we want to do transit spectroscopy to study the atmospheres of some of the TRAPPIST-1 planets. Now, I have to say that TRAPPIST-1 is a very popular and attractive system, and so many other teams are going to be doing transit spectroscopy on the TRAPPIST-1 planets. We are going to focus on TRAPPIST-1b, C, and G. And our goal for now is to determine whether those planets have an atmosphere or not, because that's something that we don't even know yet. And if we do find out that one of those planets or all of them have an atmosphere, we can maybe determine what kind of composition the atmospheres, what kind of composition those atmospheres have, and study them in more detail. And that's it. That sums up our proposal.
Great, thank you, Olivia. And I can mention Olivia is actually leading the largest Canadian James Webb project in terms of number of hours for PhD student, and there are other people that are faculty members. So that is no small feat. So congratulations for that, Olivia.
Thank you.
So next up, our final panelist, last but not least, is Maria Drought. She is an assistant professor in the Department of Astronomy and Astrophysics at the University of Toronto. Her research focuses on understanding the evolution, influence, and ultimate fate of massive stars. In particular, she uses ground and space-based telescopes to study supernova explosions and other exotic transients, as well as populations of massive stars in nearby galaxies. Maria was previously a Hubble Fellow at the observatories at the Carnegie Institution for Science and received her PhD in 2016 from Harvard University, no less.
Excellent. Thank you very much for that introduction. So yeah, I'm going to be talking to you today about my program, which is a bit different than the others. We're going to be detecting the synthesis of the heaviest elements in the universe with James Webb. So you'll have to hang on with me because it's going to be a bit of a wild ride that takes us through cosmic explosions, gravitational waves, and even the mergers of neutron stars and black holes in space. But really, there's just 3 points I want to hit on to tell you about our program on James Webb. So the first one is just that the origin of the heaviest elements in the periodic table, I swear I'm going to be talking about astronomy, not chemistry, but the origin of the heaviest elements in the periodic table have actually been quite vigorously debated for at least the last 60 years. You might be familiar with the famous saying from Carl Sagan, the iron in our blood, the calcium in our bones were made in the interiors of dying stars. We are made of star stuff. And that's very true. But it also isn't a completely solved question of how all of those elements form. In particular, we have a pretty good idea of how you synthesize elements all the way up to about when you get to iron or so on the periodic table. But all of these heavier ones I've shaded here, things that include very important elements like gold or neodymium that makes magnets or even uranium, it's been much less clear how those elements formed. We know that you have to have some very energetic process to do it. But until recently, there were actually 2 primary theories for how this could happen. One was just that you make those incredibly heavy elements in supernova explosions. So that is, I don't want to call anything run-of-the-mill in terms of astronomical explosions, but that is when a star maybe at least 10 times bigger than our own sun, when it gets to the end of its life, it's going to collapse and then explode outwards, creating lots of heavy elements. So that was one option. Another option, which is even more exotic, is the idea that you might have neutron star mergers. So what is that, you might ask? So a neutron star, you're probably more familiar with black holes, but imagine taking a black hole and then take something that's just a little less massive than that. So these are sort of the leftover remnants after a normal supernova explosion. you'll be left with a neutron star afterwards if you're not quite heavy enough to make a black hole. And so sometimes you can have two neutron stars that are next to each other and orbiting each other and eventually merge and throw out a bunch of material in their own right. So those were the two ideas of where the heaviest elements in the periodic table come from. Neither one is particularly simple to do. And also there were actually, although both were theorized to work, both actually had some bit of difficulty with them. For a supernova, there's tons of them. We see them all the time in the universe, but it wasn't clear that the physical conditions were actually right to get all the way up the periodic table. Whereas on the other hand, we thought the physical conditions should be just about right for the neutron star mergers, but in that case, they're really rare events, and we hadn't actually ever seen one. Embarrassingly enough, they should occur, but we hadn't actually seen one until, and this is my second point that I wanted to hit on for you, that all changed in 2017. So what happened in 2017? It turned out that, again, moving a little bit to physics away from astronomy, the LIGO and Virgo gravitational wave detectors, which are located here on Earth, and they're detecting like the wiggling of space-time due to gravitational waves permeating the universe, they detected gravitational waves from a neutron star merger for the first time. So they were able to say, we can tell from these tiny little wiggles in space that a neutron star merger happened over there. And when they did that, we were able to say, as astronomers, we're like, okay, let's point our telescopes in that direction. And when we did, we were able to see the fading light from an explosion that happened at the same time. And that fading light, I'm just showing you an example here of it getting brighter and then fading with time, that is actually created in the neutron star merger due to the radioactive decay of some of these heavy elements. So we were able to say from this event in 2017 that neutron star mergers definitely make some of the heavy elements in the periodic table. But there was still one remaining question. From that 2017 event, we were able to say that we make pretty heavy elements up to the lanthanides in the periodic table, but it was unclear if you actually are able to get all the way up, even further, to actually things like gold and platinum. It was still an unanswered question. So my third and final point is, what can Webb do? What is our program actually aiming to do to try and help untangle this mystery? Well, it turns out that event in 2017, we were only able to watch the fading emission and glow of light from the explosion for about 3 weeks afterwards. And in that time period, you can tell there's a lot of radioactive elements, but you can't tell how far up the periodic table you go. That changes if you can go past 3 weeks. If you can go out to 3 months after the explosion happens, then you start to see things like these green lines, the blue lines, or the dashed black line here, where basically we're predicting, depending on what exact elements you created in this explosion, very different behavior for how the light from this explosion fades between 1 and 3 months after it happened. The trick is, at that time, these things are very faint and they're incredibly cold. So what do we need to see it? We need to have a really big telescope that sees into the infrared. Basically, we need James Webb to be able to do this. So the punchline of our program is exactly what we're hoping to do is basically wait for LIGO and Virgo, these gravitational wave detectors on Earth, to find another nearby neutron star merger. Our fingers are going to be crossed so hard during that time period that it actually happens. And when it does, we're going to search again for this fading glow from the explosion and follow it with James Webb for at least 3 months afterwards, and hopefully learn a little bit more about the origin of the elements. So thank you. And that's the brief summary of our program.
Great. Thank you so much, Maria. I love astronomy. It's like, oh, supernova, that's old hat. That's like not
right?
intense enough. We need a bigger explosion. So I'll now invite all of our panelists back on, and we'll have our panel discussion now. So if at home you would like to know more about the science and the research projects that were presented here, please send your questions in the chat and the comments at the end of the panel discussion and throughout the audience session, so it'll be easy for your questions to pop up. So for the panel discussion, I have a few questions here to ask you. All three of you can answer each question, or you can skip a question if you'd like. Just feel free to chime in with your answers if you feel compelled, and you can add on to each other. It's a discussion. It's not like a really formal question period or anything like that. So the first question that I had was, what was it like to write a proposal, a telescope time proposal for James Webb? A lot of people have a vision, a certain vision of what an astronomer is, and writing proposals doesn't necessarily tie into that. So how was that writing, and how was it different from asking time on other telescopes?
All right, I guess I can go. Yeah, so basically this is not your typical telescope. We're not going to this observatory to like look into a lens or collect data directly. Rather, it's all operated by a big team who is operating James Webb and all the observations. And so how it goes is it first starts with a science idea. What do you want to learn about the universe? And once you have this idea, you want to test it out. You're like, can James Webb see it confidently? And then you have to assemble all the pieces that you need. This is a big project. You need to find the experts to sort of like fill in the blind spots that you have, because none of us are fully equipped to do all of this alone. And then once you have your team, then you kind of like put on your advocate hat and go, this is really cool science. This is going to be observable. And we have a very good team of talented people who can analyze these data. And so this sounds super grandiose, but this also happened during the pandemic. So how it was for me, it was me behind my screen, kind of like for 2 weeks straight, or like many weeks straight, kind of like thinking about this very excessively and trying to meet the deadline. So the amount of work that I did progressed exponentially as we got closer and closer to the deadline.
Yeah, I would add on to that as well. And I mean, I guess I'll give the background too that, yeah, it might not be something that people think a lot of for astronomers, but this is super common if you're actually an observer. So I know that my group, because we try to do science that spans the electromagnetic spectrum. And so we write proposals for all sorts of telescopes and different satellites. So I would say we maybe write like 30 proposals a year, actually. And so a lot of time is spent, thinking about what science we can do with instruments and putting it on. What I would say was different for me about James Webb this time is it's even just like, I don't know, the practice, right? The more times you write a proposal for a given telescope or instrument, you're just more familiar with it. You know roughly what its technical capabilities are, what science you can actually do. Whereas this was the first round of proposals for James Webb. So everything is new. And it was for everyone, for all three of us and for everyone else. So it's sort of like, it's a really sensitive infrared telescope. And we know more than that, but it's like, there was so much more work that went into figuring out, but like, what can I actually do? Or even figuring out what is a reasonable ask? And some of that is, you don't know until you see how that first time allocation committee goes. Are they going to, say, oh, that's way too ambitious for this first round? Or are they going to say, no, we want to see the biggest projects ever. And like all of these small programs, not so much. So it was like, it's very like game theory-y and figuring out what exactly you should ask for, especially the first time.
Yeah. Did you have anything to add, Olivia?
Yeah. Well, I don't know if it's really like it's just a fun story. I had a kind of a different experience in terms of like planning ahead for this proposal. I think I would say that I started planning for this proposal like much more in advance than other proposals, and that's kind of like not something I would take credit for. I was actually taking a course at the same time, and we had to like write a telescope time proposal as an exercise for that course. And so we kind of decided, my supervisor and the team and I, we kind of said like, oh, well, let's just kill two birds with one stone and write the proposal and submit it to that course and also to the real thing. So I think it turned out to be a good thing that I started earlier, because it definitely took more time than I expected. Because of what you said, that all the things were new. So I had to learn everything basically from scratch.
Yeah, and I think the fact that you were so successful, it shows that you started preparing quite a bit earlier. I can sort of speak to the other side of that. I wasn't writing the proposals. I was trying to encourage people to write proposals and encourage them to start writing as early as possible, just because the learning curve was quite steep. And for any of you at home who think astronomers are like superhuman geniuses who are like always organized and doing their everything on time, look at the number of proposals that are submitted with time, and you'll see a huge spike a few hours before the deadline. So astronomers do things at the last minute, just like normal people. We procrastinate too.
Absolutely.
So another question that I had mentioned that Canada wasn't part of the Hubble Space Telescope mission. And for Webb, we are part of it. So that's something that I find super exciting. So what does it mean for Canada to be involved in JWST, considering we haven't been involved in such a huge space astronomy mission before?
I could take a first stab at this one. And I would say it's a huge deal. I mean, being directly involved, there's at least 2 or 3 different fronts I can think of. And this is, I'm not someone who builds instruments on telescope myself. I mostly use them, but it was a huge deal in terms of jobs and development and other things that Canada played such a huge role in actually developing multiple like instruments and components of this mission itself. And then just in terms of the science, it's not that we can't propose for time on the Hubble Space Telescope. I do, other people do as well. Like several of us have used Hubble Space Telescope, even though Canada's not directly involved, but part of what it means for Canada to actually be involved in such a way too means that it facilitates more science because there is some amount of actual, I don't want to make this about money, but some funding available actually to like actually have people working on James Webb and doing the science with it. This is things that people in the US, like they would get funding if they had time on Hubble in order to actually do the science with it. And now that actually is applying for those of us who are in Canada as well. So it just like means so much more is available in terms of resources to help us do this science.
Mm-hmm. Other thoughts?
Yeah, I agree. You can go ahead.
Yeah, I also think that a very good consequence of that is that a lot of students from like Canadian institutions are going to benefit from the data, myself included. I think I'll be able to like get my hands on the data and start working on them very early on. And I think that's going to leave like a very great legacy for Canadian astronomers and the next generations of astronomers in Canada.
Yeah, exactly that. I think being involved in basically having Canada being involved in building the telescope meant that a lot of institutions in Canada thought about how to use the telescope way early as well. And so that's very exciting.
Yeah. I don't want to like toot our own horn, but something like 1/3 of all Canadian-led programs that got time are people that are associated with IREX, and IREX were really heavily involved at creating the Canadian instruments. So we had a little bit of an inside track there, and it really showed there. But yeah, hopefully it's just the start of like a whole new legacy and a new generation of astronomers in Canada who can use the James Webb Space Telescope and beyond. So we heard a little bit about your science projects, but looking more broadly at everything that Webb might do, what excites you the most about Webb? It could be discoveries or just its technical prowesses or something that it might mean for outreach. We're also Canadian, so polite.
I think, I don't know, it's one of those that it's just how sensitive it is, and looking at these new wavelengths of light are opening up a lot of different regimes for science. You mentioned a lot of them at the beginning, Natalie, in terms of things like what you can do with types of stars that we can look at. I'm someone who also studies stellar populations in nearby galaxies, and there's so much we're going to do just by taking pictures of nearby galaxies and then hoping some of those stars eventually explode as supernova, but we'll have so much more detailed information. And so it's really that combination of pushing that much further into the infrared, but being so sensitive at the same time. And, you know, I'm a big proponent of Hubble. I love seeing in the ultraviolet as well, but it's just having that new window of even further into the infrared. It just opens up new types of science. It's not just doing the science Hubble did more sensitively, it's opening up new types of things that we couldn't do before.
Mm-hmm. Yeah, I would agree with that. I think James Webb is really opening up a bunch. I would say that it's a trailblazing kind of instrument where we didn't reach the limit of what we could learn about exoplanets with the current technology that we had, but it was pretty limited in what we could learn. And now James Webb is sort of like pulling things in all directions. Some of the people are going to study the constituents of an atmosphere. Some people are going to map the atmosphere and the temperature and like look at the global climate of these planets. Some other people will go far away and explore fainter planets that we couldn't see before James Webb with other instruments. So it's really exciting, and I'm excited to see like in what direction the field is going to go.
Yeah, I would agree to all of that, and I'm also very excited to see what's going to happen. It's kind of hard for me to predict what will be like discovered with the James Webb, but I'm just generally very excited to see what we're going to learn. So I think I've seen like a couple of big programs, like 100+ hours dedicated to exoplanet atmosphere. So I think that's awesome. Knowing that James Webb is like not entirely dedicated to exoplanets, knowing that there's a big chunk of time for exoplanets, that's very, very cool to know.
Mm-hmm. Also mention that I'm like a little nervous as well, like because I'm so excited about all this science. I don't deal with suspense well, so the whole idea of like it launches and then you've got like this 2-week time period before like it's working out. Anyway, I'm almost because I'm excited. It's very nerve-wracking. So.
You're saying the real deal, like we're all being very positive, and I mean like the best minds in the world have been working on this mission, so we're all very, very optimistic about it. But like you can't help but be a little bit nervous. I'm thinking about the people who have been working on this for decades, like the majority of their career, and they're just strapping this thing on a giant rocket and then they're crossing their fingers. So yeah, we'll be happy once it's like safe and sound at its final location and ready to operate.
Absolutely.
So some of you have touched upon this a little bit when you were describing your research projects, and I think it shows what good proposal leaders you were. Astronomers and scientists in general are sometimes portrayed to be sort of like lone geniuses in media or science fiction, where they like sort of come across their ideas in these like eureka moments, but we know that science doesn't really work like that. So how would you describe the importance of teamwork and collaboration in modern astrophysics and projects like Webb?
I can go.
I was going to say, I could go off on this for a while, so maybe one of you should go first.
Yeah, I mean, it's a bit cliche, but it's very true. Like, I don't think I'd be here talking to you tonight if it weren't for like my supervisor and the team members who helped us write the proposal. And I think it's going to be the same thing when we eventually do get the data. Like, a bunch of other people are going to join us, and we're going to have help from all of them. We're going to use tools that were developed by specialists in those fields. So very luckily, I won't be alone looking at those data and trying to be a genius on my own. So yeah, I think it's necessary to work in teams in astronomy, and probably in a lot of other fields in science.
Lisa, did you want to add something before Maria goes off?
Yeah, I'll talk about it before Maria goes off. Yeah. But yeah, like I said in my little presentation, my collaborators were crucial for me in putting together this proposal. And that's because they thought of things that I couldn't think of myself. I myself am an observer. I know things about the James Webb. I know things about how to observe exoplanets, but I don't necessarily know the details of like the microphysics of the atmosphere of an exoplanet. And this is something that I can ask other people who spend most of their days thinking about this to kind of like chime in. Also, one thing that's really difficult about taking any data from any observation is once you have your images or your data, you don't really know whether what you're seeing is real, what's caused by the planet, what's caused by the star, what's caused by the detector itself. And so kind of like having a lot of people from different disciplines as well, you can sort of like get together and think about, what is it that you're seeing?
Absolutely. Yeah. And I would just say, like, I mostly think, like, it is a very common trope of the lone genius. And I even think, especially that's not the case now, but it never really was the case either. Like, people can talk about, I don't know, people like Hubble, for example, Hubble Space Telescope. Hubble was a very important person in the figure of astronomy and very, like, he learned a lot of things. He was very smart, but he didn't do it in isolation. Some of his biggest things relied on data that he himself did not take. And, it just nothing, almost no science can ever happen in isolation with one person just sitting there and thinking. There are some exceptions to that, but almost nothing that involves actual data or observations of the universe is that ever possible for. And I would even say astronomy, even compared to some other experimental sciences, does still have a little more of the apprenticeship type model where you tend to sometimes have smaller groups and you work very directly with an advisor. But even in that context, astronomy in the last few years has gone much more towards bigger programs where you need large numbers of people to run them. So like my proposal on Webb, for example, this is even without like, it relies on the LIGO and Virgo gravitational wave collaborations doing science that, there are hundreds of people involved in making those detectors work that my science would not be possible without. And then even beyond that, I had 60 plus co-authors on my James Webb proposal, because part of that is that, especially studying explosions in space, you need large numbers of telescopes surveying the sky every night. It takes a lot of people to run that. And when an explosion happens, that's your one shot at it. A few months later, it's gone. And so you really need lots of people doing things all at the same time, collaborating, working together to put all of the science together. So like my program in particular, I would say, 2/3 of the scientists who do the type of science I do, we all pooled together and submitted a series of related James Webb programs. And, they ended up going in. And part of it was we had this global set of people being like, we're all interested in this. We're not competing with each other. We're just going to put it in together. So,
yeah. There are author lists on papers out there that are like thousands long because it just took so many people working together and lots of data to make these kinds of discoveries, definitely. So we're going to wrap up the panel discussion with one question that I always like to give to our speakers. Briefly, what is one piece of advice you would give to anyone out there who would like to become an astronomer? I know there are lots of students that are watching us right now, and they might be the next one to use the great space telescope that comes after Webb. So what is something that you would tell them as a piece of advice? Lisa, go ahead.
All right. I truly don't feel wise enough in the field to to be able to give advice at this point. But truly, do it if it makes you happy. For a long time, astronomy, it wasn't necessarily something that I grew up with, but it's something that I learned along the way as I was like much older, and I fell in love with it and decided to pursue it, and it led me right here. And at moments, really, sometimes it could make you unhappy. Sometimes it could make you happy, but I don't know where I'm going with this.
It's real life. I mean, there's like good and bad things for everything.
Yeah. But overall, it's making me really happy. And what really fuels my excitement for all of this science and James Webb and my career in astronomy, it's really having people like cheering up for me and seeing people as excited about the things that I do.
Totally.
Awesome. Maria?
Yeah, I would say, this is going to seem weird, but I would say for those of you interested in becoming astronomers, my two pieces of advice for you are, first of all, totally echo, you can do it. And the two pieces of advice are, don't shy away from computers and don't shy away from things like creative writing. And the reason I'm going to say that actually is people are often shocked at how much of our jobs is actually, we gather our data, but then a lot of it's like processing it on the computer, coding, doing other stuff like that. And so just being aware of that will help you a ton in this career. And I say creative writing because the other side of it is, can't emphasize enough how any scientist these days, but especially something like astronomy, where in all honesty, none of our research is going to help the world get through a global pandemic. It is somewhat less like directly connected to what is happening in many people's lives today. But it still has a role. And a huge part of that is that we are there to inspire and engage the world in this sort of expansive knowledge of all humanity. But in order for that to work, we need to be able to communicate that. Otherwise, why are we doing it? So that's why I would say, a huge part of our job is communication as well. And you should take that seriously.
Maria knows what she's talking about. She's a founder of ComSciCon, which is a scientific communication workshop, both in the US, and she's brought it to Canada too. So listen to her. Communication, very, very important in science.
Yeah.
Did you have final words for us, Olivia?
Yeah, I don't know what else I could say. I think I would just say, just go for it. But maybe that's just my naive advice because I don't know better. I don't know. Just go for it.
Yeah, that's actually close to what I tend to answer. Like, don't assume that you can't do it because you can do more than you realize. We tend to like put barriers for ourselves, and think that we can't do it. So just give it a shot before you like assume that you can't do it or you don't like it. So thanks so much for that discussion. We're going to jump into some questions from the audience now, and I already saw quite a few that are streaming by. So again, please type in your questions in the comments or chat, depending on where you're joining us from. Nous sommes aussi heureux de prendre vos questions en français, si vous voulez. Plusieurs de nos panélistes peuvent aussi répondre en français si ça peut vous intéresser. So I'll ask our moderators to pop up our first question. So Sylvain Simard says, how long will we have to wait after launch, December 18th, before viewing a first image from the telescope? So I can actually answer this from the mission point of view. So the first image will actually not be an image that you're imagining in your mind of like a nebula or something like that, because it is such a complex mirror. It's actually a segmented mirror. So the mirror is made up of 18 smaller mirrors, and they will all have to be focused in order to be pointing at one object and get a nice clear image. So in all probability, the very first image from the telescope will be a star or a field of stars that will be focused from 18 little versions of that star or that field of star focused into one. But eventually, we're hoping near the end of the commissioning phase where we're testing all the instruments, so 5 or 6 months after the launch, we'll be able to show you some of the first spectacular images coming out of the telescope.
And I guess I'll just add on to that quickly that like, as I said, that's the timeline. And then like after the commissioning is done, a lot of that early release science that she talked about at the beginning will happen. So I think the three of us with our more general observer programs, we're sort of looking at hoping to get data like in a year, maybe like October-ish of next year or so, when our programs will start getting data.
Yeah. So to all the panelists, okay, you're told that you have X hours of observation time. How do you and your team prepared? And come the slot, what are you doing? How do you direct the observation? This is interesting.
How do we, yeah, that's a great question. Yeah, I mean, and it really comes down to, I guess, in the way this is phrased, it's like we get this much time. How do you decide what to do with it? So I think the first things, at least from my science side, we're looking at explosions as they fade over time. If you have some amount of time, like what we're trying to figure out is, okay, given the detectors, how long do I need to stare at it to detect it? And then like, can I take a spectrum? Can I take like observations like in multiple places across the wavelength? It's sort of what can I actually fit in the amount of time I have, and what is actually needed to pull out my science? And that's a huge part of what we were doing with writing the proposals, is doing it the other way and saying, okay, I want to do this one bit of science. Here, like a huge part of it is justifying how much time do you really need to do that. And you don't want to ask for too much if it's not needed, but you don't want to ask for too little lest they think you can't actually do your science with it. So it's this trade-off really of how long do I really need, and do I really need it?
One thing that I can add, the way that this question is formulated, I think this is another sort of misconception of what astronomers do. It used to be that astronomers would go to the telescope and take the data themselves. This happens sometimes still, but even for ground-based telescopes, for the most part, once you get a notification that you've received a certain number of hours, your program is programmed into a schedule, and you're not actually the one who takes the data yourself. You will hopefully get an email at some point that tells you, ding, we took your data, here it is, and good luck with your science, kind of thing. So the astronomers don't actually have to direct the telescope itself during their observations.
Yeah, like Natalie said, most of the time our observations are already kind of like planned, so we know exactly what we're going to ask James Webb to do. And how we're going to prepare on our side before the data arrives can go in two ways. And so I know that I talk a lot about having observer and theorists on my side, and that's because the theorists are going to basically like figure out what a lava planet is like. This is sort of like uncharted territories, even for the theorist. And then the observer, like myself, A lot of us are part of big programs where we get together and figure out how we're going to extract the data or the information that we want from our observations. So we're going to write a lot of code, a lot of like image processing code that is going to help us do this. But we're going to do this in collaboration to try to share the knowledge that we'll accumulate together to as many people as we can, because these data and these observations are going to be so valuable that you don't want to do a bad job at analyzing them.
Next question. Patrick asks, what needs to be found in the atmosphere of a planet to think we might have found life? The big question always, have we found aliens? So I submit this to our 2 exoplanet experts.
Yeah, I think.
Or Olivia, especially.
I can say a few words. Yeah. So just to clarify, so for the TRAPPIST-1 planets, of course, it's very interesting because we know that some of the planets are in the habitable zone of the system. So right away, our mind goes to, oh, is there an alien on that planet? But for now, for our program at least, we just plan to determine whether those planets have an atmosphere or not. This is just like the starting point. Of course, ultimately, we want to know if there might be life or there might have been life on that planet. And I think like one way to determine this is if you think about Earth, the atmosphere on Earth has a lot of oxygen, and if there was no life on Earth, it would be very difficult or like almost impossible to have so much oxygen in the atmosphere. So that's an example of a biosignature, or a key clue that's telling us that there's life on this planet. So if, for example, we were to find like a lot of oxygen on some planet and we were not able to explain the presence of such a big amount of oxygen on that planet other than with like the presence of life, I think that would be a good indicator. Of course, we always have to be careful because there can be other like chemical processes that can produce stuff and then make us think that we found life, but it's actually just some weird chemistry going on. Yeah.
Yeah, finding alien life won't be like a yes or no answer right away. It's going to be like a maybe, and then another maybe, and then a stronger maybe. Lisa, did you have something to add?
Yeah, so a couple of years ago, this question came up at one of our exoplanet conferences, where basically we were sort of thinking about how do we define life and how do we define how we found life? And the answer is, this is also a very interdisciplinary question, right? Because we're astronomers, we understand stars, we look at the sky, but we don't know much about biology or the origin of life or like, the anatomy of a lot of living things on Earth. And so I think we're going to be able to answer the first few questions or find the first like evidence, or not evidence, but clue that there might be life. Like, for example, finding a lot of oxygen on some atmosphere, or finding chemicals that wouldn't be produced by like normal geophysics and geochemistry. But then once we find these sort of like a constituent of the atmosphere that sort of tells us that maybe there might be life, then we're going to have to pass the question to, I don't know, chemists or biologists who are going to pursue this quest of finding life for us.
Definitely. Our next question. What downstream technologies and industries might benefit from the techniques, technologies, and materials used to build Webb, or the information learned from your experiments and others? So yeah, often we get this question like, what is astronomy good for in everyday life? Maria, did you want to speak to this a little bit?
Sure. Yeah. I mean, and I think there's two sides of it, right? There is this, like, what about the techniques and materials? And then there's the information from our experiments. So like from our science side, I mean, some of this is like mine. I'm learning all about how do the heaviest elements in the periodic table get synthesized. These are elements that we find here on Earth and are very useful, and are all about how do you actually make those. Now, often what we think is you have to make them in very extreme like physical conditions that aren't possible to reproduce here on Earth, but they are telling us a little bit about something, even, you know, things like uranium probably were necessary to do things like, we think it might be important for plate tectonics, which might be important for the formation of life, which therefore, you know, learning where those elements come from might tell us more about where those types of things are possible in the universe. But again, that's very, like, not direct. Whereas, I don't know, just the infrared technology that was used to make Webb does have a ton of other applications, both in other things that happened before it was developed in order to get to this point, and now in things you can do with that afterwards. So I would say, like, a lot of that detector development has been very important, whereas the science results on ours are much more on the sort of fundamental aspect of our knowledge.
Yeah, definitely. Next question. Quelles sont les chances d'observer une collision d'étoiles à neutrons durant la vie de James Webb? So this is actually a question for you, Maria. What are the odds of observing a neutron star collision during James Webb's mission lifetime?
This is an incredibly good question, and one that we had to justify quite a bit in our proposal. Because, yeah, I mean, unlike everyone else's program here, where, like, the planets you guys are supposed to look at, like, TRAPPIST-1 exists. Like, we know that it's there. You will definitely be able to look at it. Our program is something we call a target of opportunity, where it is something that it didn't exist when I wrote the proposal. We're just hoping that it does occur. So we know more about how frequently neutron star mergers happen from previous gravitational wave runs. So we had to include lots of calculations in our proposal about how likely is it that we will actually be able to trigger this once James Webb happens. And I mean, the punchline is, there is a lot of uncertainty in this, but all of our calculations showed that we are likely to get between 1 and 2 of these events per year while the mission is going. So I would say over the 5+ years of Webb operating, the chances are really good. Are we actually going to get one during that first year when our program is active? It's unclear. And so part of that was we asked for actually it to be a long-term program that at least covered the first 2 cycles so that we'd have a higher probability. But it's pretty good, but it's not 100% that it will actually happen.
All right. We'll keep our fingers crossed for you.
I know. So many fingers crossed.
Yeah. The next question, how well do you think your observations on James Webb will be complemented by the soon-to-be in operation Earth-based giant Magellan or extremely large European telescopes? So the complementarity between space-based telescopes and the giant ground-based telescopes that are coming up in the next decade. So Maria, I can sort of, it's not a giant telescope, but like certainly I can imagine you're going to be very interested in the Vera Rubin telescope for transients, right?
Yes, absolutely. And so I would say that things like the Vera Rubin Observatory, which will come online soon, will help us find all of those explosions. So I said, in order to, you know, see the fading light from this, we have to know where it is first. And James Webb is not a surveying telescope. It's not going to find the fading light from a neutron star merger. We have to find where the source is with something else like Vera Rubin or other things, and then we can point James Webb at it. So other missions will be very critical for it. And then these very large telescopes, I would say the huge thing is they will also let us probe very faint things, but again, more in the optical light, because we can't see the same region of the infrared that Webb can do from the ground. So it'll be very complementary at the same time.
Yeah. I could add that in terms of detecting life or those first biosignatures, the fact that these telescopes are 30 or 40 meters wide and so sensitive, they might actually be good to either detect the first biosignature or support a detection made on Webb. So the more telescopes detect a biosignature, the more chances you have that the signal is actually real.
Yeah, I'll also add that these like ground-based telescopes are going to be bigger than James Webb as well, or some of them are going to be bigger. And one of the things that Olivia and I have talked about, we're going to observe transiting exoplanets. So we're not taking a direct picture of these exoplanets, but rather the star and the planet at the same time. But these big ground-based telescopes, we're going to start being able to image directly these exoplanets, and not just those that are super far away from their star, but closer in as well.
Yeah, so similar to the Earth system, the Earth-Sun system. So the next question. Considering the deployment will be done during traveling to final destination, why not deploy it near Earth orbit in order to test/repair and then launch the telescope to its final location? So this is a good question, and I do get asked this a little bit. So in order to start braking and making the telescope go and stop and go, you're actually using up fuel. And fuel is actually the limiting factor for the lifetime of the mission. So in order to like stop it there and then eventually make it go launch again, you would severely limit the lifetime that James Webb would have, because it requires propellant to keep it stable in its orbit. That's why we're hoping at least 5 years, maybe up to 10 or 11 years. But if we were to stop it in low Earth orbit to make sure it deploys properly and then make it go again, that would use up a lot of fuel, and we wouldn't be able to actually have a very long mission. So instead, what we do is we test it very, very, very thoroughly here on Earth, so that the deployment does happen smoothly once it's launched into space. Next question is, will JWST be able to detect population 3 stars in the early universe at extreme redshifts? What's the redshift limit of James Webb? Maria, I don't know if you know a little bit about this.
Yeah, so there's a couple things we can talk about here. So yes, James Webb will be able to see into the very early universe. Whether or not, I would say it probably won't detect a star in the way you're thinking of, where like you see an individual object and we know that's a population 3 star. Part of it is that actually we are detecting light from, for instance, the galaxies that are that far away. However, you don't see individual stars or objects once you're probing that distantly. However, there are people who are hoping to use James Webb, and also the Roman Observatory, which will come on soon, to detect the explosions of those population 3 stars. Then the idea being that we think those stars should be somewhat different than the stars we see now. So like very massive, and they might create very energetic explosions. So if you can detect a supernova explosion that is incredibly luminous and coming from those very distant galaxies, there might be evidence that that could be the explosion of a population 3 star. So that's something people are hoping to do.
Mm-hmm. I can add that in terms of redshift limit, I'll talk instead about the age of the universe that we're observing. Hubble was able to look back to about 500 million years after the Big Bang. Webb will be able to push it to about 200 million years after the Big Bang. Now, 200 million years sounds like a really long time, but keep in mind that the universe is around 13.6 billion years old. So it would be the equivalent of if you put the entire history of the universe on one year on a calendar, you could, and you are December 31st, you'd be able to look back at about January 6th. So that's really early on in the like cosmic calendar of the universe. So not quite the Big Bang, but we're getting pretty close. So this will be the last question here for Olivia. Why in your proposal did the team not go for planets D, E, or F, which are also in the habitable zone of TRAPPIST-1, and they were closer to Earth's environmental temperature and space conditions with maybe liquid water?
Yeah, that's a very legit question, and I kind of suspect that it would come up tonight. But the answer is very boring, unfortunately. As I said, there are a couple of other teams who are also going to look at TRAPPIST-1 and do transit spectroscopy, so like exactly the same thing as we'll do. And those teams are going to look at TRAPPIST-1, D, E, and F, so exactly the planets you're referring to. So we're not just probing like the other planets. Our goal was also to get like a better family portrait of the TRAPPIST-1 family, and so I don't think it's like irrelevant to observe the planets that are not like in the typical habitable zone. And so yeah, the main goal is to get like a better portrait of all the planets together so that we can understand the system as a whole better.
Yeah, but because of all the teamwork, you will probably end up getting a little bit of that data too from the teams that are observing those planets.
Yeah, definitely.
Yeah. So unfortunately, that's all the time that we have tonight. So I'd like to thank Carolina, Marie-Ève, and Frédéric for all their help in organizing and managing the event and moderating the chats and talking to you throughout the night. A huge thank you to you, Lisa, Olivia, and Maria for being with us tonight, giving us a taste of what we can expect with the Webb telescope and telling us more about yourselves and your passion for space. If you like what you saw tonight, do like and follow us to learn more about all of our upcoming events. I can mention in particular, we have an event coming up in November in French. At IREX, we have an annual talk, and it's usually given by an astronomer coming from somewhere else in the world. But because of the very exciting launch of James Webb happening at the end of this year, we will be hosting our director, René Doyon, who is also the principal investigator for James Webb in Canada. And he's been working on the project for 20 years. So if you think we're nervous about James Webb, he is really, really nervous about the deployment. I don't think he's going to sleep for the entire month it's going to take for the telescope to get to its final destination. So the event will certainly be live streamed, but we're hoping to have a limited in-person audience at the Campus Mille of the University of Montreal. So stay tuned for details on that, either on our website or our Facebook page. And save the date now. So November 17th, 2021 at 7:30 p.m. So I'd like to thank our generous donors, in particular the Trottier Family Foundation, without whom our activities, both at IREX and MSI, cannot be possible. And finally, a big thank you to all of you listening tonight or at any other time. This video will be available to rewatch on our Facebooks and YouTubes. So thanks again. Merci à tout le monde. Have a wonderful evening and keep December 18th in your calendar. We'll all be following Webb's launch and the science that's going to be coming up in the next years very, very closely. Bye, everyone.